Hello everyone, this is your course instructor Monisha Raj KH, Assistant Professor, Department of EC, Sai Vidya Institute of Technology. In this lecture video, we'll be continuing with Module 1 of Information Theory and Coding. Today, we'll be studying about average information content of symbols in long dependent sequence and Markov statistical model for information sources. First, let us see what is average information content of symbols in long dependent sequences. Nearly all practical sources emit sequences of symbols that are statistically dependent, that is, sources have memory. For example, the letter E occurs more frequently than letter Q. Occurrence of letter Q implies that the following letter will most probably be the letter U. The occurrence of a constant implies that the following letter will most probably be a vowel, and so on. This statistical dependence or structure reduces the amount of information coming out of such a source compared to the amount of information coming from a source emitting the same set of symbols in independent sequences. The problem we address in such situation is one of the calculating the information rate for discrete sources that emit dependent sequences of symbols or messages. For this, first develop a statistical model for sources emitting symbols in dependent sequences, and then using this model to define the entropy and information rate for the sources. And this statistical model used is Markov statistical model. So this is about the average information content of the symbols in long dependent sequences. Next, we'll be seeing the entropy and information rate of Markov source. HI is defined as the average information content of the symbols emitted from the ith state. Therefore, HI equal to summation j equal to 1 to n Pij log of 1 by Pij to the base 2 bits per symbol. This is the HI, that is the average information content of these symbols. Next is the entropy of the source is then the average of the entropy of each of the states. That is, H equal to summation I equal to 1 to n Pi Hi bits per symbol, where Pi is the probability of the source in state I. This is about the entropy of the states and the entropy of the source. Next is, this is the example for a Markov model. Next is the average information rate RS for the source, which is defined as capital RS equal to small rs into h bits per second, where small rs is the number of state transition per second or system rate of source. If P of Mi is the probability of a sequence Mi of n symbols from the source, only if Gn equal to 1 by n summation I equal to 1 to n P of Mi into log of 1 by P of Mi to the base 2 bits per symbol, where the sum is overall sequences Mi containing n symbols, then Gn is monotonically decreasing function of n. Hence, limit n tends to infinity, Gn will always be equal to h, that is the entropy, bits per second. These are the important formulas that we use in the numericals, which we are seeing further. Next, we'll start with the numericals. First numerical, for a Markov source shown in the figure, find the entropy of each state, the entropy of the source, the third one is G1, G2, G3, and show that G1 greater than G2 greater than G3 greater than H. Draw the tree diagram representing the states at the end of second symbol interval and find corresponding probabilities P of 1 equal to P of 2 equal to P of 3 equal to 1 by 3. This is the Markov source model for the problem. First, they are asking you to calculate the entropy of each state and is given by the entropy of each state Hi equal to summation j equal to 1 to n Pij log of 1 by Pij. That is h1 equal to p11 log of 1 by p11 to the base 2 plus p12 into log of 1 by p12 to the base 2 plus p13 into log of 1 by p13 to the base 2. For example, p11. What is p11? It is a state transition from state 1 to 1. That is, from the Markov source model, p11 is, it's a state transition from 1 to 1. P12 is the state transition from 1 to 2, that is 1 by 4. P13 is the state transition from P13, that is, these are the probability values for those state transition. So substituting these values, we get H1 as 1 by 2 log 2 to the base 2 plus 1 by 4 log 4 to the base 2 plus 1 by 4 log 4 to the base 2. Calculating it, H1 will be 1.5 bits per symbol. That is taking the state probabilities from the Markov source model. This is for the entropy of the state 1. Next, we need to calculate the entropy of state 2 and state 3 with the probability values. H2. H2 equal to P21 log of 1 by P21 plus P22 log of 1 by P22 plus P23 log of 1 by P23. In the similar way, substituting the probability values for the state transition, we get H2 as 1.5 bits per symbol. Next is H3. That is P31, a log of 1 by P31 plus P32 into log of 1 by P32 plus P33 into log of 1 by P33. Substituting the state probability values for the same, we get H3 as 1.5 bits per symbol. This is how you calculate the entropy of each stage, that is state 1, 2 and 3 from the with the help of Markov source model. See, P21, this is the P21 value, P22 the self transition, and P23, that is, this is the probability value. Substituting these values, we get H2 and H3. Next, after calculating the entropy of each state, we need to calculate the entropy of the source. So entropy of the source is given by H equal to summation I equal to 1 to 3 Pi Hi. So H equal to P1 H1 plus P2 H2 plus P3 H3. So substituting the H1, H2, H3 calculated values and P1, P2, P3 which is given in the question, that is 1 by 3, we get H as 1.5 bits per symbol. Next in the question, they are asking you to draw the tree diagram with the help of Markov source model. So how do you do that? This is the Markov source model. So first, we need to draw the tree diagram for state 1. So P of 1 is 1 by 3. So for state 1, you will be drawing three states, that is 1, 2 and 3. Again, for state 2, again for this state, we'll be drawing 3 states. For this state, we'll be drawing 3 states. And for this state, we'll be drawing 3 states. This is the tree diagram for state 1. So the transition of from state 1 to 1 is 1 by 2. See, from this Markov source model, the transition from state 1 to 1 is 1 by 3. 1 by 2. From 1 to 2, it is 1 by 4. From 1 to 3, it is 1 by 4. This is how you write these values. So how will you get these values? That is, this is the initial state. This is the state at the end of the first symbol interval. This is the state at the end of the second symbol interval. How will you get to know where to stop? In the question, usually they would have asked you to stop at the second symbol interval or first symbol interval. As in the question, they have not mentioned anything. Kindly stop at second symbol interval. So how do you get the values at first symbol interval? The multiplication of the values at 1 by 3 into 1 by 2, 1 by 6, 1 by 3 into 1 by 4, 1 by 12, 1 by 3 into 1 by 4, it will be 1 by 12 again here. Again, the values for transition of state 1 to 1, 1 to 2, 1 to 3, 2 to 1, 2 to 2, 2 to 3, 3 to 1, 3 to 2, 3 to 3. This is from the Markov source model. You'll get these values. That is from 2 to 1, it is 1 by 4, 2 to 2, it is 1 by 2, 2 to 3, it is 1 by 4. Those values, you'll write it here. Now again, you need to calculate these values. It will be 1 by 6 into 2, 1 by 12, 1 by 6 into 4, 1 by 24, 1 by 6 into 4, 1 by 24. Multiplication of 1 by 12 into 1 by 4, 1 by 48. So by multiplying the first symbol interval into the state transition probabilities, we get the second symbol interval. And by multiplying the initial state and into the transition probability, we get the first symbol interval. So this is how you write the tree diagram. This is for the state 1. For state 2, you do it the similar way. Take state 2 at the beginning. The probability of state 2 would be 1 by 3. It is given already in the question. So again, write three states, 1, 2, and 3, and these are the transition states. Write it with the help of Markov source model. Again, write the values by calculating 1 by 3 into 1 by 4, 1 by 12, 1 by 3 into 1 by 2, 1 by 6, 1 by 3 into 1 by 4, 1 by 12. You'll get the probability values at these first in symbol interval, and again for the second symbol interval, follow the same procedure. This is for second state. Similar we will do it for the third state. That is initial state, state at the end of the first symbol interval, state at the end of the second symbol interval. This is how you draw the tree diagram for Markov source model. Next, they are asking you to calculate G1, G2, G3. How will you do it? To find Gn, this is calculated only based on the tree diagram. So Gn equal to 1 by n summation I equal to 1 to n p of mi log of 1 by p of mi to the base 2. So first n1. I'll show you how to calculate everything. This is calculated based on the tree diagram. How will you do it? G1 is for the initial state. G2 is for the state at the end of the first symbol interval. G3 is the state at the second symbol interval. Okay, initial state values. Here I am showing only one tree diagram. For this calculation, you need to consider all the three diagrams, all the three tree diagrams. So first for G1, we'll be calculating it with the help of probability values at the initial state. So at all the three diagrams, the initial state value is 1 by 3, 1 by 3, 1 by 3. So substituting the probability values as 1 by 3, 1 by 3, 1 by 3, we get G1 as 1.58 of 585 and substituting n as 1. At the second state, that is at n equal to 2, G2. That is, you will be calculating the probability values for these states. Kindly remember, you need to consider it for all the three tree diagrams. Here I am showing only for the first tree diagram. So it will be 1 by 6, 1 by 12, 1 by 12, 1 by 12, 1 by 6. See, for the third tree diagram, it will be 1 by 12, 1 by 12, 1 by 6. So considering the probability values of all the tree diagrams at the first symbol interval and substituting it in the equation, we get G2 value at G2 value as 1.5425 bits per symbol, and here n would be 2. That is substituting in this equation. This is how you calculate G1, G2 and G3. So now G3 value in the similar way. How will you calculate it? By considering the last, that is a second symbol interval. Considering these probability values, you will calculate G3. So kindly remember, this is for G3, these values are for G2, and this is for G1. So calculate G3 by substituting the probability values. You will get it as 1.528. After calculating, they have asked you to prove G1 greater than G2 greater than G3 greater than H. So hence it is proved. That is 1.8585, 1.425, 1.525, 528, 1.5. Hence proved. This is how you calculate the entropy of each state, the entropy of the source, draw a tree diagram and calculate G1, G2 and G3. Next we'll move on to another numerical. A card is drawn from a deck. You are told it is a spade. How much information did you receive? How much information did you receive if you are told that the card is an ace? If you're told that the card is an ace of spade, how much information did you receive? And the fourth one is the information obtained in third the sum of the information obtained in 1 and 2? So they're asking you to draw a card from the deck and calculate the following. So let us see how to calculate it. There will be 52 cards in a deck, right? So with 13 spade, ace, 2, 3, 4, 5, 6, 7, 8, 10, KQJ. Similarly, 13 hearts, 13 cloves, 13 spades, and diamond shaped cards. First question is, they're asking you about the spade. So since there are 13 cards in a deck of 13 spades in a deck of 52 cards, so P spade will be 13 by 52, 1 by 4. So they're asking you to calculate self-information. So self-information of I spade is equal to log of 1 by P spade to the base 2. So log 4 to the base 2, 2 bits. In the second part of the question, they're asking you to calculate it for ace. So there are 4 A's in a deck of 52 cards. So P A's equal to 4 by 52, that will be 1 by 13. They're asking you to calculate the self-information of the same. So I A's equal to log of 1 by P A's to the base 2, log 13 to the base 2, it will be 3.7 bits. In the third case, they're telling you that the spade card which you take is a ace. So there is only one ace of spades in a deck of 52 cards. So P ace of spade equal to 1 by 52. That is self-information of the same would be I ace of spade equal to log of 1 by P ace of spade to the base 2. So log of 52 to the base 2 will be 5.7 bits. This is how you calculate the self-information for a spade, for ace and ace of a spade. The fourth part of the question, they are asking you to calculate if sum of the I ace of spade should be equal to the sum of the self-information of the spade and ace. They're asking you to prove that. That is, as the information obtained in the third one is the sum of the information obtained in 1 and 2. That is, the total self-information must be equal to individual self-informations of that are obtained in 1 and 2. So I ace of spade equal to I spade plus I ace, that is 5.7 equal to 2 plus 3.7, that is 5.7 equal to 5.7. This is how you calculate the values for spade, ace and ace of spade, and the sum of the values, that is the total self-information must be equal to individual self-information values. This is how you prove it. Next question is, next numerical. Consider the state diagram of the Markov source. Compute the state probabilities, find the entropy of each state, and find the entropy of source. In the previous question, when we saw about the Markov source, they had already given you the state probabilities. But here they're asking you to calculate the state probability values. So this is the Markov source model, what it is given. State probabilities means the probability values for these states. In the previous diagram, it was 1, 2, 3. So they are already given P of 1, P of 2, P of 3. But here they are asking you to calculate these state probabilities. So how will you calculate? Let's see. From the state diagram, state equations can be written as, so now you need to write the state equations. So remember, how will you write the state equations? You need to consider only those transition probabilities that are coming to that state. So P of A equal to 0.6. 0.6 is the self state transition. So you'll be considering that. So 0.6 of PA and only 0.5 is coming to A. So you'll consider it as 0.5 into PD. That is the first equation. For B, see, you'll be only from A, you are getting the state transition from A and D. So you'll be considering only those values. That is P of B equal to 0.4 into P of A plus 0.5 into P of D. See, that is the equation. Kindly remember, you need to consider only those transition lines that will be coming to that state while writing the state equations. Then for P of C it is coming from B and it has self state transition. So P of C equal to 0.5 into P of B plus 0.6 into P of C. That is third equation. Next is P of D. For P of D, kindly remember it is in this diagram, the arrow mark should be towards D. So P of C in zero point 0.4 into P of C plus 0.5 into P of B. These are the four state equations. From these state equations, you need to calculate P of A, P of B, P of C and P of D. So how will you do that? This is a state diagram. Equation 1. From the equation 1, you can simplify equation 1 to 0.4 P of A equal to 0.5 P of D. So P of A equal to 1.25 P of D. Next, from equation 3, equation 2 cannot be further simplified. So we are moving on to equation 3. 0.4 P of C equal to 0.5 P of B. So P of C equal to 1.25 P of B. So then substituting in equation 4, these values. So P of D equal to 0.4 into 1.25 into P of C plus 0.5 into P of B. So P of D equal to 0.5 into P of D. This should be P of D. Kindly change it. This should be P of D. So plus 0.5 into P of B. So P of D equal to P of B. You will get these relationships from equation 1, 3 and 4. So now you need to calculate the values. How will you do that? Let's see that. So P of A equal to P of C equal to 1.25 into P of D. First we'll see we know that P of A plus P of B plus P of C plus P of D equal to 1. That is, the probability values for each of the states will be equal to 1. So substituting the values for P of A, P of B, P of C and P of D. That is 1.5 P of D plus P of B is equal to P of D. We have already found it from equation 4. And 1.5 into P of D plus P of D equal to 1. Now substituting 4.25, by adding, we get 4.25 into P of D equal to 1. So P of D value we get it as 2 by 9 and P of B value we get it as 2 by 9. Now substituting these P of D values and P of B values in P of A equal to P of C equal to 1.25 into P of D, we get it as 1.25 into 2 by 9, that is 5 by 18. So we have calculated the state probability values. We know P of A, P of B, P of C and P of D. Next is, they're asking you to calculate the entropy values of each of the state. So first is H of A. H of A, here you need to consider all the probability values, not only one that are coming to the A. So PA log of 1 by PA to the base 2, PAB log of 1 by PAB to the base 2, PAC log of 1 by PAC to the base 2, PAD into log of 1 by PAD to the base 2. PA is 0.6, PAB is 0.4. There is no PAC and PAD. So make these two values as 0. Substitute only 0.6 and 0.4 and calculate. So you'll get HA as 0.971 bits per symbol. Next is H of HB. PAB into log of 1 by PAB to the base 2 plus PBB log of 1 by PBB to the base 2, PBC log of 1 by PBC to the base 2 plus PBD into 1 by PBD to the base 2. So PBA, there is no value. PBB, there is no value. There is value for PBC and PBD. That is 0.5, 0.5. Substitute and calculate. You will get HB as 1 bit per symbol. HC in the similar way. Substitute the values for CA, there is no value. CB, there is no value. CC, there is value. CD, there is value. So 0.4 and 0.6 substitute and calculate, you get 0.971. HD, there is value for DA and DB. There is no value for DC and DD. So only substitute values for DA and DB. So you will get it as 1 bit per symbol. Next is entropy of the source. Summation I equal to 1 to 4 Pi Hi. So it will be PA into HA plus PB into HB plus PC into HC plus PD into HD. Substituting all the values, because we have calculated all the values, we get it as H of S equal to 0.9839 bits per symbol. With this, we'll be computing module 1 of information theory and coding. Thank you.